And welcome to Chapter 13, Section 2, Theoretical and Experimental Probability. And try these, come back and check your work. 1/4 is 25%. 2/3 is 66 2/3%, or you could have written 67%. 37.5 and 100%. And for your permutation, we have 120, and we have 20. And 35 for your combination, and 28. So today we're going to find the theoretical probability of an event and the experimental probability of an event. The vocabulary today. I think we've discussed most of these things, and you have not used them a lot, so this is a good practice day for you. So the measure of how likely an event is to occur is probability. And each possible result of a probability experiment or situation, each result is called an outcome. So a group of possible outcomes is known as the sample space. The sample space. It's the whole set of possible outcomes. For example, on rolling a number cube, the numbers 1 through 6 are possible outcomes, so they are the whole sample space, right? And an event is an outcome, or a set of outcomes. So on a die, rolling a number is an event. On a spinner, spinning a color is an event. All 4 colors are the sample space. And probabilities are written as fractions or decimals from 0 to 1, or even as percents. So let's say flip a coin. The probability is, on a fair coin, 50% that you'll get heads or tails, right? 1/2, or 0.5. When you have the same chance of an outcome occurring, we call that equally likely outcomes. So as I just said, when you toss a fair coin, heads and tails are equally likely outcomes. Favorable outcomes are outcomes in a specified event. So for equally likely outcomes, the theoretical probability of an event is the ratio of the number of favorable events to the total number of outcomes. For equally likely outcomes, the probability of an event equals the number of favorable to the number of total. Each letter in the word probable is written on a separate card. The cards are placed face down and mixed up. So what is the probability that a randomly selected card has a consonant? How many possible outcomes are there in all? Well, we just count the letters, right? So there are 8 possible outcomes. And how many are in favor of a consonant? So you would go back and count out your consonants or subtract away your vowels, right? And we see there are 5 favorable outcomes. So the probability of randomly selecting a consonant is 5 of 8, or 62.5%. If 2 number cubes are rolled, what is the probability that the difference between the 2 numbers is 4? So we see if we roll 2 number cubes, how many total possible outcomes are there? And we see there are 36. And then we have to identify how many of these pairs have a difference of 4. So we look for those, and we see that we would place that value over 36. So see what you can find and give me the probability. And you should have found 4 of 36, or 1 in 9 outcomes have a difference of 4. The sum of all probabilities in the sample space is 1. So back that up. The complement of an event, E, is the set of all outcomes in the sample space that are not in E. So in other words, if I have a coin and I flip it, there's a 50% chance I'll get heads, and there's a 50% chance I'll get tails when we add the two together. 0.5 and 0.5 equals 1, right? So the complement of flipping heads would be flipping tails. The probability of the complement of an event, so the probability of not event E would be 1, and then subtract the probability of event E. So if I have, let's say, a coin again, and I know the probability of getting heads is 50%, the probability of not getting heads is 1 minus 50%, or 50%. There are 25 students in a study hall. The table shows the number of students who are studying a foreign language. What is the probability that a randomly selected student is not studying a foreign language? So, what is the probability that a student is not studying a foreign language? We know this number of students is, and there are 25 students in the hall, right? So the probability can be found by using the complement, 1, and let's subtract the probability of a student taking a foreign language, and that would give us the difference of 1 and 21/25, since there are that many taking the language, or 4 out of 25, which is 16%. So there is a 16% chance that the selected student is not studying a foreign language. I guess the other way to find that would simply be subtract this total from 25, and that is 4, right? 4 of 25. Go ahead, and I'm going to pause, and you pause and see what you can come up with here. So did you decide, is this a permutation or a combination? Does order matter? Yes, it does, doesn't it? So this is a permutation. And so let's find the total number of arrangements in the sample space. And so again, we have a 5-digit locker combination. And so each of the digits is a possible number, and we have 10 digits, right? So we see that we end up with 10 times 10 times 10 times 10 times 10, or 100,000 possible outcomes. We now need to find the number of favorable outcomes, right? So how many of these digits could be odd, right? So we know that there are 5 odd digits, right? Possible for each digit in the 5-digit code. So when we put that together, we see there are 3,125 odd. Those are our favorable outcomes. So to find the probability, we take our number in favor, 3,125, over the total possible, and we can reduce. So the probability that a combination would have only odd digits is 1 out of 32 combinations. So a form of theoretical probability determined by lengths, areas, and volumes ratios is known as geometric probability. A figure is created placing a rectangle inside a triangle inside a square, as shown. If a point inside the figure is chosen randomly, what is the probability that the point is inside the shaded region? So we're going to find the ratio of the area of the shaded region to the area of the entire square. The area of a square is simply a side squared, and you know the area of a rectangle is 1/2 of base times height. The area of a rectangle is length times width, or base times height, right? So let's find the area of the entire square. And we can see that each side is 9. So the area of the square is 9 squared, right? Or 81. And these are centimeters squared. And so let's find the area of the the triangle. And the triangle has a base of, that's right, 9, and the height of 9 as well, doesn't it? And so we can take half of 9 times 9, or 40.5. Now we've got to kind of cut out, because this triangle is not entirely shaded, we have to cut out that little rectangle in there, right? And so we can see that this height of the rectangle is 4 and the base is 3. So we're going to take that away from the shaded area. So the area of the rectangle is 12. Subtract that from the shaded area, 40.5, and we have 28.5. So the shaded area over the total area gives us the probability that we would find that point, right, which is 19 to 54, or 352 thousandths. You can estimate the probability of an event by using data or by experimenting. For example, if a doctor states that an operation has an 80% probability of success, 80% is an estimate of the probability based on similar case histories. Each repetition of an experiment is a trial. So flipping a coin is a trial. The sample space of an experiment is the set of all possible outcomes. So the experimental probability of an event is the ratio of the number of times that that event occurs, frequency, to the number of trials. So we know on a fair coin that there's a 50% probability of getting heads, right? There's also a 50% probability of getting tails. Now we can find, that's a theoretical probability. We can take a coin and start flipping it and see how many times we do get heads or tails and find the experimental probability. If we have a large enough trial sample set, right, then we should approach the theoretical probability of 50% if we flip that coin enough times. So experimental probability is actually doing the experiment and finding the number of times that the event occurs and placing that over the total number of trials. So experimental probability is often used to estimate theoretical probability and to make predictions, right? So here's a table that shows the results of a spinner experiment. Find the experimental probability. Spinning a number greater than 2. So we have 4 numbers on the spinner, and notice they spun the spinner and ended up with these results. So what would the theoretical probability be, or I'm sorry, the experimental probability be for getting a number greater than 2? So we see that these numbers are greater than 2, so how many times did we get 3 and 4? It looks like 33 times, right? 33 out of how many total spins were there? We've got to count them all up. So we have 50 total spins. So 33 out of 50 is 66%, right? So it seems like we got these numbers 3 and 4 66% of the time. Now theoretically, if this was a fair spinner, how many times would you expect to get the numbers 3 and 4? About 50% of the time, right? So this shows you the difference between theoretical and experimental probability. Go ahead and try the quiz. Come back and check your work. Number 1, 88%. And number 2. And lesson quiz 2. And the experimental probability is 55%. Good job. Have a good day.